Hello. As promised, we are going to record a video that addresses the points that will be covered on your final exam for the Chemistry 1046 lab at West Campus, Miami-Dade College for the spring semester of 2024. So in this pH graph, we have pH on the y-axis, and then we have volume of sodium hydroxide on the x-axis. And as you can see, all the graphs look essentially the same. The difference is that when this graph is for a strong acid with a strong base, the beginning of the pH is much lower because the strong acids are fully ionized. So the pH is less, and the graph is going to have a larger change because starts very low. Okay, but the equivalence point, which is the point in which the number of moles of the acid equals the number of moles of the base, so they basically neutralize each other, is this point over here. And at this point, you're not going to have any acid and you're not going to have any base. The number of moles of those is 0. But instead, you're going to have the conjugate acid, the conjugate base of the weak acid. So this is the only species that is going to be present at the equivalence point. All this section here is called the buffer section. The reason why it's called the buffer section is because during all that time that you're adding sodium hydroxide to a weak acid, as long as your sodium hydroxide is the limiting reactant, then you're going to have an excess of the weak acid, and then you're going to have the conjugate base of the weak acid being formed. So as long as we keep sodium hydroxide as the limiting reactant, remember, as long as you are before the equivalence point, the sodium hydroxide, which is the titrant, is what you're adding, is going to be in limiting. So you're going to have an excess of the acid, that obviously some of the acid would be consumed, but you're going to have an excess of the acid unreacted, and then you're also forming the conjugate base. So when you have these two together present, you have what is called the buffer. So during all this time, you're going to have a buffer system. However, since your equivalent point in this titration is reached when the volume of sodium hydroxide is 24, half of that volume, which is 12, is the point in the graph right here where the concentration of the acid equals the concentration of the conjugate base. Because you have consumed half of the acid and you have produced half of the conjugate base that you're supposed to make. So this point here is called half the equivalence point. So at half the equivalence point, the concentration of both the weak acid and its conjugate base are equal. Before that, before the half of the equivalence point, so during all this section here, the concentration of your acid is always going to be greater than the concentration of the conjugate base. And after the equivalence point, which is this section here, the concentration of the acid is going to be less than the concentration of the conjugate base. Let me make that bigger so that you guys can see it well. So once again, at the half of the equivalence point, the concentration of both the weak acid and the conjugate base are the same because you have added half the moles of the base than you had acid. So for example, if you have 0.1 moles of the acid to begin with, you have added 0.05 moles of the sodium hydroxide. So therefore, your sodium hydroxide would be completely consumed and you're going to consume only half of the acid, so you're going to be making half of the conjugate base. And to explain that even better, for example, let's say that you have a weak acid reacting with sodium hydroxide, forming the conjugate base plus water. For example, let's say that you started with 0.1 moles of your sodium, of your weak acid, sorry. And then let's say that you add half the number of moles of the base, okay? And of course, you have none of this to begin with. This is the beginning. Let's call it B, beginning, or before. And then during the change, obviously, since this is your limiting reactant, your reaction is a 1-to-1 ratio, you're going to be consuming all of the sodium hydroxide. So at the end, or after, if you want to call it after, you're going to have no sodium hydroxide left because it's going to be consumed. That's why over here, there is no OH present. All the OH here has been consumed. You're only going to consume half of your weak acid, and then at the end, you're going to still have the other half that has not reacted yet. But in here, you are producing, remember, your limiting reactant is responsible not only to determine how much of the other reactant reacts, but it also determines the amount of the conjugate base that is produced. So at the end, you're going to have 0.05 of the conjugate base. So as you can see, as long as you add half the moles of the strong base of the acid that you have, as long as this number is half of that, you're going to end up with the same number of moles of your weak acid and your conjugate base. So at that point is what we call half the equivalence point. It's very easy to find this point here, because all you need to do is look at your graph, find out what the volume of sodium hydroxide was needed to neutralize your weak acid, and then divide this number by 2, go up to the graph, and that would be half of your equivalence point. So at that point, once again, the concentration of the weak acid and its conjugate base are equal. Before that, you have more acid than conjugate base, and after that, you have less acid than conjugate base. But at all this time, during all this time, you have both of them present. When are they're going to disappear? You're going to disappear when your acid is completely neutralized by the sodium hydroxide. Then here, all you're going to have is your conjugate base. And once you pass the equivalence point, so any of these points here on this section here, all you're going to have is excess of base. That's why if you're doing the titration with phenolphthalein, for example, it turns really pink. 1 drop of the sodium hydroxide makes it converts your solution from a very light pink to like fuchsia. And it's because you have an excess of sodium hydroxide. And phenolphthalein turns pink in the presence of sodium hydroxide. Okay, so that's more or less your titration graph. Now let's specifically talk about a question that I have here. It says the graph above represents the titration of 80 milliliters of a 0.150 molar solution of a weak monoprotic acid. This is an important word because monoprotic means that your reaction between your weak acid and your conjugate base and your sodium hydroxide is a 1-to-1 ratio. Okay. So it says, using the graph, what is the pH of the acid before the addition of the sodium hydroxide? So that means at this point, what would be the pH of the acid? And you can see from here that the pH of the acid looks like it's 2. All right. So the second question is asking, what is the molar concentration, or what is the concentration of the hydrogen ion in the acid? So how do we get the concentration of the hydrogen ion in the acid? You guys remember that pH is equal to the negative logarithm of the concentration of the hydrogen ion. Well, we do have the pH, but we don't have this. This is what we're looking for. So to solve this equation for this, we need to first multiply both sides by -1. So we get minus pH equals log of the concentration of the hydrogen ion. And then we need to use the function that is the opposite to logarithm, which is 10 to the x. So we're going to have 10 to the minus pH will be equal to the concentration of the hydrogen ion. So all we need to do is raise 10 to the power of -2 because your pH is 2. And that would be the concentration of the acid of this hydrogen ion in your acid. Okay. Now, if this number were to be 3, then this would be 1 times 10 to the -3. If your acid will start in 2.5, then it would be, the pH will be 2.5, and this would be 1 times 10 to the -2.5, and then you just use your calculator. So just for the sake of argument, let's say that your graph actually starts here. Okay, so let's pretend that the graph starts here for a second. So in that case, your pH will be 2.5. And then this will be 1 times 10 to the -2.5. Now, how do we solve that? Okay, so in that case, you enter, you see, I don't know what kind of calculator you guys are going to use, but if you use something like this, the 10 to the x is the opposite function to the log. So you enter 10 to the, and then you enter -2.5. And then you just press enter and it will give you the number. Okay. In our case, since the pH was 2, you just do 10 to the -2. Obviously, you get 0.01, which is 1 times 10 to the -2. So that is the concentration. This just, doesn't apply. That's just an example of if it's not exactly 2, how to solve it. Okay, so we got the concentration of the hydrogen ion. Now remember that the concentration of the hydrogen ion is also the concentration of your conjugate base. Okay, so let's keep that in mind. All right, so calculate the molar concentration of the sodium hydroxide. Calculate the molar concentration of the sodium hydroxide. In other words, what is the molarity of the sodium hydroxide? So this is when you need to use the volume of sodium hydroxide, and you also need to use the volume of the acid that we started with and the concentration of the weak acid. So we need to start with these two because that's what we know of. So converting your 80 milliliters to liters, it will be 0.0800 liters. Let's try to keep the significant figures alive. And then you're going to multiply that by the concentration of the acid. Let's call the acid HA, divided by liters. That's your concentration. This is going to give you, once you cancel the liters, it's going to give you the moles of the acid. And then you're going, knowing that it's a monoprotic acid, you know the reaction is a 1-to-1 ratio. So this is now going to give you the moles of sodium hydroxide. So that would be 0.08 times 0.15, and that is going to give me 0.012. And I'm going to put another 0 there to just keep my significant figures alive. So that would be the moles of the sodium hydroxide. But remember, the question is not asking for moles. The question is asking for molarity. So now we need to take that number of moles and we need to divide it by the volume that was used in the titration. So that means 0.0120 moles divided by, notice that in your titration, we use 24 milliliters of sodium hydroxide. That's when the equivalence point was reached. So that was the volume that was used, and we need to use that in liters. So then you get the molarity of the sodium hydroxide. So that would be the final answer. Okay. For letter D, it says, what is the species in higher concentration at each labeled point? If more than one species is present, compare the concentration and give the name of the specific point if applicable. So in point A, let's call this point A. Let's call this point B. Let's call this point C, any point in here. Let's call one here point D, and let's call this one point E. So point A, B, C, D, and E. Okay, so in point A, that is called the equivalence point. That would be the specific name. And then in there, you have present just the conjugate base is the only thing that is present in there. Of course, you also have the spectator ion, which would be sodium and water, but those do not affect the pH. So usually when we said the species that is present is only the species that really affects the pH. Okay, so point B over here is what we call half the equivalence point. And at half the equivalence point, we're gonna have acid, but we're also gonna have the conjugate base, and the concentration of both is the same. And point C was before that. So point C is any point in here. So that means in point C, you are before half of the equivalence point. Before half of the equivalence point. So at that, during that time, you do have both the acid and the conjugate base. Remember, sodium hydroxide is your limiting reactant. However, you still have more acid than conjugate base because you have not reached the half. Point D is past half of the equivalence point. And then once you pass half, then the concentration of your acid is going to be less than the concentration of the conjugate base. Again, at no time during any of these 4 points, you're going to have sodium hydroxide. The sodium hydroxide is your limiting reactant all the way up to the equivalence point. And then finally in point E, when you're past the equivalence point, you're past the equivalence point, then of course in there, you're gonna have an excess of the strong base. So that's why the strong base is going to determine. Okay, so one question that always comes to mind is what is the approximate pKa of the acid? Explain your selection using the Henderson-Hasselbalch equation. Okay, so let me make this a little bigger so you guys can see the question. It says, what is the approximate pKa of the acid? And explain your selection using the Henderson-Hasselbalch equation. Okay, so graphically, you go to here, you go half of the equivalence point, and then you go to the pH. And notice that it's a little bit under 4, so I'm going to call it 3.9. So the pKa is about, it's asking for the approximate, so 3.9, 3.8 will work. Now, the reason why you could do that is because the Henderson-Hasselbalch equation, which looks like this. This is going to be the concentration of the acid at equilibrium, and here is the concentration of the conjugate base whenever at that position on the graph. So what happens at half of the equivalence point is that these two are the same. So when you divide two numbers that are the same, this fraction here becomes 1 because you're dividing equal numbers. And the logarithm of 1 is 0. So all this factor here becomes 0. So your pH equals your pKa. So only when you are at half of the equivalence point is that your pKa of the weak acid can be determined graphically from the value of the pH. So once again, notice that what I did was this is your equivalence point. This is your half of the equivalence point because it's half of 24. You go up and then you find the pH, and that is going to be the pH of the solution at that point, half of the equivalence point, which is equal to the pKa. And you just explain it using the Henderson-Hasselbalch equation. So with words would be, at half of the equivalence point, these two numbers are the same. The concentration of these two is the same, so that this factor becomes 0 because the log of 1 is 0. So these two become equal. So it says at the equivalence point, is the pH greater than, lower than, or equal to 7? And then it says, give an equation that explains your selection. Okay, so if you notice in your graph, this is the equivalence point. You notice that the pH is greater than 7. So the pH at half of an equivalence point, not a half, but at the equivalence point is greater than 7. Also notice that at that point, you only have the conjugate base. That's the only thing that is present at the equivalence point. So to answer this question, you says the pH at the equivalence point is greater than 7. Now, remember that at the equivalence point, the only species present is the conjugate base of the weak acid. And the conjugate base of the weak acid experience what is called hydrolysis. That means reaction with water. And because this is a conjugate base, the conjugate base is going to do what bases do, which is take away a hydrogen from water, remove a hydrogen from water, forming the weak acid plus OH minus. Now, this is called basic hydrolysis and equilibrium. This is called basic hydrolysis. Notice that it forms OH. And this is the reason why at the equivalence point, the pH is greater than 7. All right, so I'm going to use this opportunity to talk about what is the equivalence point, what is the pH at the equivalence point for a reaction between a strong acid with a strong base. So the pH at the equivalence point of a strong acid with a strong base is always 7. And the reason for that is because since when the two of them neutralize each other, you're making what is called a neutral salt. For example, if you have hydrochloric acid reacting with sodium hydroxide, hydrochloric acid, this is an H, reacting with sodium hydroxide, that forms sodium chloride plus water. Because sodium chloride is the salt that comes from a strong base and a strong acid, this is a neutral salt. It does not experience hydrolysis. So the pH at the equivalence point is due to the Kw of water. Now remember, the Kw is 1 times 10 to the minus 14. So that means the concentration of OH minus equals the concentration of H plus at 25 degrees Celsius. And that's going to be 1 times 10 to the minus 7. which is why the pH is 7. But that is only true when you have a titration between strong acid and strong base. If your titration is between a weak acid with a strong base, that pH is always going to be greater than 7. pH will always be greater than 7. Here, pH is going to be 7. Here's going to be greater than 7. And the reason for that is because at the equivalence point, the conjugate base of the weak acid, which is the only thing present, is going to experience basic hydrolysis, which means it's going to rip the hydrogen from water, forming OH minus. And because of that, the pH is greater than 7. And when you have a strong acid with a weak base, in that case, the pH at the equivalence point is going to be less than 7. And the reason for that is because you're going to have the conjugate acid of the weak base. Let's call it B plus, because if your weak base, for example, let's say that you have hydrochloric acid reacting with ammonia. Let's write ammonia as NaOH so that it's easier for you to see. So in that case, you're going to form ammonium chloride. But the ammonium chloride is not a neutral salt because ammonium ion comes from a weak base. So that ammonium ion is going to experience acidic hydrolysis because it's a conjugate acid of the weak base. And here is the conjugate base of the weak acid. So your conjugate acid of the weak base, if this is the example, that would be ammonium, reacts with water, and it's going to form your base again, plus the hydronium ion. Okay, so let's say that this is Hb plus, so it's going to donate because that's what acids do. They're going to donate to water. Here, the base is going to take away from water. So here, the conjugate acid is going to donate to water, and it's going to it's called acidic hydrolysis. So this is acidic hydrolysis, while in this case is basic hydrolysis. But in our specific case, because it's a weak acid with a strong base, the conjugate base, which is what we have here at the equivalence point, experience what is called basic hydrolysis. And that explains why the pH is greater than 7. Okay, so the next question says, calculate the exact pH of the titration when 16 milliliters of the sodium hydroxide have been added, and then use the calculated concentration from part C. So remember, the calculated concentration from part C for sodium hydroxide was 0.500 M. All right, so they want us to calculate the pH, the exact pH of the titration when we have added 16 milliliters of sodium hydroxide. Why is this question asking for the exact pH? Is to avoid you guys from going here, going up, and then estimate this pH. I want to know the exact pH. So what you need to do here is you need to do the reaction. So remember, we started with, let's go back to our beginning, 80 milliliters of 0.15 molar solution of the weak acid. So let's calculate the number of moles of the acid. It's 80 milliliters times 0.15 moles per liters. So this is 0.012 moles of the acid. This is what we have. And then what is the number of moles of the sodium hydroxide that we are adding? Well, they want us to do it for 16 milliliters. So that would be 0.016 0.016 times the concentration of sodium hydroxide was 0.5. 0.016 times 0.5, it's going to give me 0.008. That is the number of moles of sodium hydroxide that I'm adding. Okay, so you can see here that when you have the reaction between the weak acid plus the sodium hydroxide, which forms A minus plus water, if you started with 0.012 and 0.008 and no conjugate base, this is your limiting reactant. So you're going to be subtracting that from both reactants and adding that in your product. And then, of course, you're going to end up with no sodium hydroxide. You're going to here end up with a little bit of the acid left. And here you're going to end up with conjugate base. And then to find the pH, since the presence of a weak acid and the conjugate base means that you have a buffer. If this is completely consumed, then you don't have a buffer anymore. And that will only happen when you are at the equivalence point. But as long as you have a little bit of the weak acid and conjugate base, you have a buffer. And you need to use the HH equation to calculate the pH. Now, what concentration do we use? Well, technically, we're supposed to recalculate the concentrations. So the concentration of your acid is, because this is concentration of the conjugate base over concentration of the acid. So the concentration of the acid is going to be the number of moles of the acid divided by the total volume. So the total volume is the 80 milliliters plus the 16. So that's 0.96 milliliters, or 0.96 liters, sorry. So you take the number of acids, the number of moles of acid left, you divide it by the total volume, and that's going to give you the concentration of the acid. And similarly, in the same way, you're going to take the number of moles of the conjugate base, which is 0.00800. You're going to divide it by the total volume. And I'm going to address something right now. Let me just finish this. Divided by 0.096. So this is going to be 0.0417. And this is going to be twice as much because the numerator is twice as much. So that times 2 is going to give you 0.0833. Now, you can avoid doing this because notice that you're dividing both moles by the same volume. So if you avoid doing that, because you're dividing numbers that are, this fraction is going to be the same whether you use the moles or whether you use the molarity, because the moles are divided by the same volume. So this divided by this is going to be the same as this divided by this. And I could prove it to you. So 0.08 divided by 0.04 is 2. 0.0833 divided by 0.0417 is also 2. It cannot get any closer than that. So we can avoid having to do this step, and we could just go straight from substituting this number here and this number here. Now that only works if you are doing a titration. If you're preparing a buffer from the two components, like separate components, then it's different. So here your pH is going to be, remember the pKa, we estimated to be, what was the number for the pKa? 3.9 over here, plus the log of, so it's going to be 0.0833 divided by that, Or you could use 0.008 divided by 0.004. Either way, you're gonna get this, it's gonna be 2. So the log of 2, it's 0.301. So pH is gonna be 3.9 plus the log of 2, which is 3.9 plus 0.301. So your pH went up to 4.2. 4.201. So that would be the exact pH of your solution when you added 16 milliliters. And if you think about it, that is pretty much what you're gonna get in here. If you extrapolate this to the y-axis, that's more or less, because this is 16, is a little bit higher than 4, as you can see. So that would be more or less what you will get by estimating from the graph. Now, the next question says, calculate the exact pH of the titration when 32 milliliters of sodium hydroxide have been added. And then again, use the concentration from part C. So we're going to use the number of moles of the acid. We already calculated that. It's 0.012. And then now the number of moles of sodium hydroxide is 32 milliliters. So that's 0.032 liters times 0.5 moles per liters. So that would be 0.016 moles of the sodium hydroxide. So you can tell that you're now past the equivalence point, because in the reaction between HA plus OH minus, forming A minus plus water, if we do the same analysis that we did here, you started with 0.012, and you started with 0.016, and you started with 0, and then now your HA is your limiting reactant. So you're going to subtract that. So you're going to end up with nothing of the acid. You're going to subtract this. So you're going to end up with a little bit of extra sodium hydroxide. And here you're going to add. So you're going to have a little bit of your conjugate base. However, once you pass the equivalence point, the amount of basicity that your conjugate base is going to give you is insignificant compared with the excess of the sodium hydroxide. So since you are past the equivalence point, how do I know I am past of the equivalence point? Because I have an excess of sodium hydroxide now. So this point is past the equivalence point. I'm over here now, 32 milliliters. You see 32? This is where we are right now. So what is the only species present? OH. So then the OH is the one that is going to determine the pH, which means we need to calculate the concentration of OH by dividing the number of moles of OH that we have left after reacting with the acid by the total volume. And remember, the total volume is going to be the 32 milliliters plus the 80 milliliters that we're starting with. Remember, we started with 80 milliliters of the weak acid. So 80 plus 32 gives you 112 liters. So 0.004 divided by 0.112, that gives you 0.0357. That's your molarity. And then we need to get the pOH, because obviously this is a base. So negative log of 0.0357 is going to give me 1.44, 1.45. That's pOH. So then pH is going to be 14 minus that. 14 minus 1.45 is 12.55. And that would be the pH at that point. So if you notice, at 32, it's almost 13. So it's a little off in there, but that's pretty much how you calculate it. Okay, so I think I have addressed acids and bases and pH extensively. You don't expect the test to be only on this. Obviously, there are other topics that we are addressing, and here is one of them. Okay, so this is again more pH. Sorry, more equilibrium of acids and bases. So here says the molecular formula of malic acid, a diprotic acid, is C4H6 O5. Says the first acid dissociation is represented by the equation below. The pH of a 0.0100 molar of malic acid is measured at 3.27. This is the equilibrium reaction of the diprotic acid. So you have two hydrogens that are acidic plus water forming, this is the first dissociation. Okay, so the first dissociation is the loss of one hydrogen. So the acid is going to donate one of the hydrogens to water. It's going to form the hydronium ion, and then it's going to form the conjugate base of malic acid. Now it says, write the expression for the equilibrium constant for the reaction above. So remember, equilibrium constant for an acid is going to be the concentration of the products times C4H4O5 negative, don't forget the negative charges, divided by the concentration of the acid, and water is not going to be present. Okay, letter B says calculate the value of the Ka. Now, to calculate the value of the Ka, you need to get the value of these guys. Now, we do have, so you could do a nice table here. You said H2C4H4O5 plus water at equilibrium is going to give you the H plus, and it's going to give you the conjugate base. Let me do this in the back. So you have the acid, 5, plus water in equilibrium, forming the hydronium ion plus the conjugate base. Okay, and the initial concentration of malic acid was 0.01. So 0.01 is the initial concentration. And initially you have none of this. Then, of course, this guy is going to dissociate. So you're going to lose some X from here, but you're going to be making X's here. And then at equilibrium, it's going to be 0.01 minus X. And here you have X and X. So you're going to substitute this in the Ka. And then you're going to substitute this in the denominator of the Ka. So the concentration of hydrogen ion is X. The concentration of your conjugate base of malic acid is also X. These two numbers are the same. And then this is 0.01 minus X. So going back here, your Ka is going to be X times X divided by 0.01 minus X. But we don't have the value of X. However, we do have the pH. So just like in the other problem, we could find the concentration of the hydrogen ion by finding by using the pH. So let's do that. The concentration of the hydrogen ion is going to be 10 to the negative pH, just like we did on the first question. So that's going to be 10 to the negative 3.27. We're going to enter that in the calculator. 10 to the negative 3.27. Press enter, and you get 0.000537. That is your concentration of the hydrogen ion, which is your X. Okay, so the Ka is going to be 0.000537 square. Let me remind you why it's square, because these two have the same value. Okay, so that means your x's are the same, you square that, and then the denominator is going to be 0.01 minus 0.000537. So let's do that math. 0.000537 square divided by 0.01 minus 0.000537. And the answer comes out as 1, 2, 3, 4, 5, 3.05 times 10 to the negative 5. So that is the value of the Ka. Okay. Question C says, what is the pH of the buffer solution prepared with equal concentrations of malic acid and the conjugate base? Explain. So, how do we find the pH? Remember that based on, if you have equal concentrations of this, your pH is going to be equal to your pKa. And the reason for that is because from the HH equation, we just explained this, but I'm going to do it again. From your Henderson-Hasselbalch equation, if the concentrations of these two are the same, that means this fraction here is 1, and the logarithm of 1 is 0. So all this turns to 0, which means pH is equal to pKa. Now we don't have the pKa, but we do have the Ka. So pKa is the negative log of the Ka. So your pKa is going to be the negative log of 3.05 times 10 to the negative 5. And then you just enter that negative log of 3.05 times 10 to the negative 5. That gives you 4.52. So if your pKa is 4.52, then your pH, when these two concentrations are the same, is 4.52, because your pH equals your pKa when these two concentrations are the same. Okay, letter D says, write the balanced net ionic equation for the reaction that occurs when 5 drops of 2 molar nitric acid are added to the buffer solution in C. Okay, so it's a buffer, which means your pH is going to change, but only slightly. And you're adding an acid, so you expect the pH to go under 4.52, but not too much, okay? So your pH is gonna decrease. But they're asking for the chemical equation. So out of these two, which one is going to react with the acid? The acid or the conjugate base? The answer is the conjugate base. So your conjugate base will be the one reacting with the nitric acid. And since you want the net ionic equation, you're going to ignore the nitrate because that becomes your spectator ion. And you could put H plus or you could put H3O plus, whichever you want. and that's going to form your acid. If you put the hydronium ion, then here you're going to have to put water. But if you only put H plus, then you don't need to put water. Again, if you only put H plus, then this is going to be only the answer. But if you put H3O plus, then you also need to add water. And then letter E says write the balanced net ionic equation for the reaction that occurs when 5 drops of 2 molar sodium hydroxide are added to the buffer solution. So now you're adding a base, sodium hydroxide, to your buffer, which means which of these two is going to react with the base, the acid or the conjugate base? And the answer is the acid. So you're going to write the acid, and you're going to write the conjugate, the strong base, again, ignoring the sodium because sodium is a spectator ion. The strong bases are dissociated. And then acids are going to behave as acid, which it means it's going to give hydrogen to water, forming the conjugate base plus water. So give the hydrogen to OH, forming the conjugate base plus water. Okay. Going on to another topic, here we have this is involving KSP, which is also part of the test. So here we have MOH3 in equilibrium with M3 plus and 3OH minus. So here's obviously it's a metal that has a 3 plus charge. So it says the dissolution of M hydroxide is represented above. What is the expression of the KSP for that compound? So KSP is going to be equal to, KSP is just another constant, equilibrium constant. So you cannot have solids in your equilibrium constant, which explains why your KSP is only going to be the concentration of the ions. And in this case, the OH is going to be raised to the power of 3. So it's going to be the concentration of M3 plus times the concentration of OH to the power of 3. If this were to be a hydroxide of 2 plus, for example, then this would look like M2 plus OH minus to the second. Okay, so that is if. If, then your KSP would be equal to the concentration of M2 plus times the concentration of OH to the second. But the one we have is 3, so that would be the expression for the KSP. And then the next question says 30 milliliters of a saturated solution of the hydroxide. This is very similar to the question, to the lab that you did, was titrated against 0.100 molar hydrochloric acid. And it took 4175 milliliters of the hydrochloric acid to reach the equivalence point. Write the balance equation that represents the reaction of the hydroxide with hydrochloric acid. So they don't need you to have the net ionic equation. They just want the balance equation. So you could write the whole thing plus hydrochloric acid forming MCl3 plus H2O. Now, how do I know it's MCl3? Because obviously it's 3 plus. Okay, so we need to do some balancing here. So that is the balance equation that represents a reaction. And then letter C says calculate the OH in the saturated solution. So we know that it used 4175 milliliters of this acid to neutralize the base. So to find out the concentration of OH, we need to use the titration data. So starting with the volume of the acid times the concentration of the acid. Remember, this is hydrochloric acid. And now we need to cross to OH. So it's going to be 3 in the denominator, and then 1 mole of OH in the numerator, because it's a 1-to-3 ratio. I'm sorry, that is 1 mole of MOH3, and then in 1 mole of MOH3, you have 3 moles of OH. So this is going to give you the moles of OH. That's going to be all right. So write the balanced net ionic equation. Let's use the balanced net ionic equation, because hydrochloric acid is not going to react with the solid. Hydrochloric acid is going to react with the OH present in solution. So I'm going to change this question to write the balanced net ionic equation that represents a reaction of the OH with hydrochloric acid. So now we have a better understanding of this. So you're going to have just 3, you're going to have the HCl here. Here you're going to form Cl minus, but the HCl, you could have Cl minus. So anyways, it's a 1-to-3 ratio, because you have 3 OHs per H plus. So this here, we don't need to do. It's going to be OH. So divided by 3. So this number was supposed to be 0.00139. Those are the moles of OH that we're going to have in solution. And then for the concentration, we're going to divide the moles by the volume. So the volume was 30 milliliters. Divided by 0.03, and that gives you 0.0464 M. Okay, so now it says calculate the value of the KSP for MOH3. So we need to go back to the expression of the KSP. Let me just rewrite it here. Which means it's going to be the concentration of M3 plus and the concentration of OH. We do have the concentration of OH. The concentration of M3 is going to be 1/3 of this number. Because remember, if this concentration here is 0.0464, then this is going to be 1/3 of this. So this number here is going to be 0.0464 divided by 3. That will be your concentration of M plus times 0.0464, which is the concentration of OH minus, to the third. So 0.06464 square times 0.06464 divided by 3. So your KSP is 3.33. times 10 to the negative 5. Okay, the last topic that would be on the test is on the colligative properties, which is what the last experiment that we did this week. So it says the molar mass of a covalent non-electrolyte compound is to be determined. 41 grams of the covalent compound was dissolved in 200 grams of water, and the solution was cooled to freezing point. The solution achieved freezing point at negative 4.12 Celsius. The molar freezing point depression, that's your KF, for water is 1.86. What is the molality of the compound in water? So remember what molality is the moles of the solute divided by kilograms of the solvent. Okay. But we don't have the moles of the solute, and we do have the kilograms of the solvent, because we have the grams of water. So what is the other way to find molality? Well, we have the equation delta T equals KF times the molality. We do have the delta T because water freezes at 0 and it froze at negative 4.12. So my change in temperature is 4.12. That's how much the temperature changed from 0 down to negative 4.12. That means the change in temperature was 4.12 equals 1.86, which is the KF times molality. So your molality is going to be 4.12 divided by 1.86. 2.215. I'm going to round this to 2.22. And that is, remember, moles of the solute divided by kilograms of the solvent. Now the question is asking to determine the molar mass of the compound. So let's see what we have. We have that your compound has a mass of the solute given in the problem is 41.0. So in order to get the molar mass, we need to divide the mass by the number of moles. We don't have the number of moles. Okay, but we could get the number of moles because we have the molality and we have the kilograms of the solvent. So if we take the grams of water and we change it to kilograms, that's going to be 0.200 kilograms. And now we multiply that times the molality, which is moles of the solute over kilograms of the solvent. This is going to give me the moles of the solute. Now I could take this number, put it here, divide 41 by 0.444, and I get the molar mass of my compound. And with that, I end up the review for the final exam. So your final exam is going to be all FRQ questions, no multiple choice. Make sure you bring a calculator because obviously you're going to have to use one. And Good luck.